think those that are calcium-based would be more susceptible to acid degradation, but it's been a while since you looked at these things. I believe all of the carbonates are susceptible to HCl, at least, but calcite and aragonite are definitely. Dolomite, actually, you might be right, because dolomite has magnesium and calcium and CO3. So instead of all calcium, it's got a mix. It's like half and half. Half magnesium, half calcium, almost perfectly. And you actually do have to scratch that mineral a bit more to get it to effervesce. So you might actually be right. You were probably right about that. So I don't know how much less the other carbonates would effervesce or how much more than the calcium-bearing ones, but that's a really good and interesting point to bring up. But and it even goes so far as to affect the various rocks that they're in. So dolomite-bearing sandstones versus calcite-bearing sandstones. Let's say you have a calcite-cemented sandstone versus a dolomite-cemented sand. The dolomite-cemented sand, you're going to have to scratch a lot to get it to fizz, whereas the calcite should be able to just fizz with dropping some HCl on it. Carbonate-bearing carbonate-bearing blue schist facies metamorphic rocks. Those are one of the environments in which these can occur. So, I know that sounds like a bunch of jargon, right? Let's pretend that I didn't even say that. You guys know what a metamorphic rock is. It's a rock that's been put under tons of heat and pressure, or at least a lot of pressure and or heat, and it then realigns its crystals inside itself. I'm glossing over this grossly, and it makes a completely different rock. So in the case of this type of blue schist facies, that just means, by facies, it means basically the pressure temperature conditions. So in this case, in a metamorphic case, you can find aragonite occasionally in high pressure, low temperature metamorphic regimes, which is really interesting to me. You can find aragonite in areas of high temperature metamorphism. Now, remember earlier I said that, high pressure. That does not make sense to what I said earlier, because at high temperatures, it's typically altered to calcite. Despite the high pressure stability field, aragonite typically forms at near surface in low pressure conditions. One of the ways in which also this can precipitate is in calcareous mud and all sorts of cool marine environments. And all that means is that there's calcite-rich mud, all right? Or critters that died in the mud with calcium-rich shells. And then eventually those shells broke apart and became a part of the mud, and it's just this goopy mud ooze on the bottom of the ocean floor. Sometimes it's siliceous in the case of radiolaria. Depends on the type of critter that dies. Some of them are silica-rich, some of them are calcium-rich. So there's some difference there, but it can happen. You can make this gross mud because of critters that die that are calcium-rich shells. It's pretty cool too. And a lot of shells of critters can actually be aragonite. And some of the mother of pearl that you see on those shells is actually just aragonite. It can also fill vesicles in basalt and another type of volcanic rock called andesite. It doesn't matter if it's just a volcanic rock, but basically this is a good crystal. This looks clear right here. This one looks really nice and clear. But basically, all in all, and it also can form in oxidation zones like we talked about. So all in all, it can form in metamorphic environments, it can form in sedimentary environments, and it can form even in igneous environments randomly in vesicles of specific igneous rocks. So that type isn't as common, but the sedimentary I thought was most common, and then metamorphic, but so this is, again, aragonite under a microscope. I wonder if this one crystal here is pretty clear. This one right here. I want to get it in the center if I can. So some of them are pretty clear, but I don't have very many. I would love to have a sample that is, but you can actually zoom in. Might be able to zoom in even farther. Oh, wow. Oh, wow. You can see the striations very, very nicely. Look at that. You see that, guys? You can also see some superficial pits, but the lines are striations, and those are really cool. So I'm trying to get a better angle on this one. This one's kind of got some mud in it, but not too much. I wish that I could eventually, God, I wish I could play with my SEM from Cal State. It's not my SEM, but I wish it was my SEM. This is such a really, really nice sample. Here's some mud. Here's some of the mud that's likely inside of the crystalline structure as well. I'm afraid to wash it. Although this isn't soluble in water, if it's, yeah, I'll probably wash it. It's pretty vitreous, though, all in all. I want to check this guy out. I haven't looked at this one. I don't think he was as vitreous. I think it was more resinous and luster. So his index of refraction would be slightly less, probably closer to the 1.5 rather than the 1.7 we saw. Oh, here. This side's got some nice striations as well. Ooh. And I want to pull this up on Mindat. There's some better pictures I can show you. I won't be able to show you with a microscope on their end, but... See, dude, I feel the same way, Pharaohvax. Whenever I'm showing my minerals sometimes, I feel like I'm on the QVC channel. And look at these nice. I have these wonderful hands to show you all of these minerals. It's like, I don't know what it is, but it's just like, for 3 easy payments of $99.99. You know what I mean? Right, Aragonite group. Strontianite, witherite, more strontianite samples. Again, this is just because these actually form, I believe, solid solution series, in that strontium, barium, and lead can replace for the calcium in aragonite, like we talked about. So cerussite is the lead-bearing variety. So you've still got the CO3 at the end. Instead of calcium, however, you have lead, Pb. This actually shows some of the various shapes of the mineral. This is just basic prismatic, but oftentimes these will grow together and mimic a hexagonal shape. This sometimes is, this is the pseudo-hexagonal twinning that you can sometimes see. So it looks, because of a variety of the same shape growing together in twins, it makes it appear like it's a hexagonal shape. So cerussite's the lead-bearing variety. Of course, these images are always going to be really, really great. It's going to be the best of the best. If you look down to actually purchase some of these are also some of the best images. Not always, but it at least gives you more variety of what the specimens can look like. By the way, Aragonite does fluorescent or UV light. Health risks. Contains lead. Wash hands after handling. Avoid inhaling dust when breaking. So you can actually see the health risks on Mindat. Free aura. Mindat.org is amazing. I love it. So it's I think I might have scared people in when I put on gloves one of the times handling some of the toxic minerals that I have. That's just because I'm lazy and I didn't want to wash my hands and I didn't want to deal with it. I still wash them afterwards. I probably go above and beyond for safety. Yeah, I probably go above and beyond for safety. And the other reason I do that is because it's the internet, and I'm oftentimes worried that some random is just going to pop in for 5 minutes, see me holding a toxic mineral, and then think that it's okay and then just leave. You know what I mean? And I know it's probably not going to happen. It's just an irrational fear, but I actually genuinely care about some people sometimes, I guess, whatever. Ugh. And I don't want anybody to die because of my stream, ideally. If fluorite and spinel can both grow hugely, mineral grow in that shape, or only specific... No, a lot of minerals can grow in that shape. It is only specific minerals, but there are a lot of minerals in each of the 6 crystal classes. And even some polymorphs can be in multiple crystal classes, like calcite and aragonite. The reason that they're different is because although they have the same chemical formula, one is in the trigonal crystal class, and the other is in the orthorhombic. So it's a chemical composition that determines how it grows. Yeah, basically. The bonds, the ions present, that all determines. And sometimes the heat and the pressure in the system as well, Nini. And then also you have the situation where, let's say you don't have space for a mineral to actually produce its shape. It'll just fill that crevice. For example, calcite, although it does have a specific shape, it sometimes just fills spaces, and whatever that shape is the shape it takes. And it still has that crystal shape. You just don't see it with your naked eye because it didn't have the opportunity to form that way. But on the microscopic scale, it is. Just not with your naked eye can you see it. Oh, this is one of the graphs I wanted to show you with increasing temperature to the right on the x-axis and going up on the y-axis, you see increasing pressure. So this is the line that divides where aragonite will actually transform or alter into calcite. So calcite's actually really stable at high temperatures. And remember, earlier I said that at around 400 degrees Celsius, in arid environments, that's when aragonite actually starts to alter to calcite. So aragonite is also very, very good in high temperature or in high pressures, and it forms sometimes in even metamorphic high pressure regimes. So this makes sense with everything that we've learned tonight. I like having the images to summarize everything at the end. It makes me happy. I don't need aragonite. I have some. Witherite is the barium end member. Strontiumite is the strontium member. Oh, this is just mineralogy on the aragonite stuff. That's that. It's dynamic periodic table. Aragonite group. I want to keep cerussite up for later. Wait, I have cerussite. I don't need it. I have a tiny piece. I forgot. It's a very, very nice piece, actually. Doesn't look like this, but